Hi friends, so today we begin lecture 18 in our math question bank series, and today I'm going to discuss some questions in 3D geometry. So essentially we are going to look at the sphere, cylinder and some of these important geometrical figures. We are going to look at the aspects in 3 dimensions. I am Dr. Ganguly. So let's begin with question 1, very simple warm-up question, and this question asks you: there is a sphere of diameter 1 meter. It fits inside a cube such that it touches all 6 faces. And you are asked to find the area between the sphere and the cube. So this is the question. Now, whenever such a question is given, you have to essentially form a math model in terms of a diagram and then solve this problem. Now, this question we can pose as follows. Essentially, if we look at a two-dimensional view, maybe a front view of this problem, we have the cube and we have the sphere. Now in 2 dimension we essentially see a square and we see a circle. Now of course the cube has been given the dimensions of 1 meter. So essentially we can see that the diameter of this circle or the sphere is 1 meter and the side of the cube is also 1 meter. Also remember the diameter is twice the radius, so we know d equals to r. So we can clearly see that the volume of this particular region, which is colored in blue, that's going to be d cube minus 4 by 3 pi r cube. So we can write this in this manner. Remember d is 1 meter, so I put 1 here, and radius is half meter, so I put half here, and then I simplify this particular expression. So 1 cube simply becomes 1, and here we get 4 here, we get 8 here because 2 cube is 8, so 4 cancels out here, so we get 3 into 2, that is 6, so 1 minus pi by 6, and you can calculate this to be 0.4764 meter cube. So that's the solution. Now this is a good warm-up problem where you have brought in this particular volume of a sphere, that is 4 by 3 pi r cube. So that's going to lead to the next question, which is how do you derive this formula? So that's question number 2, which is derive the formula for the volume of a sphere of radius r, and this formula is known to be 4 by 3 pi r cube. This is a sphere. It's got diameter of 2r, that is twice the radius. So this is a question which you can do using integration. Now we are going to do this problem in 2 ways. The first way is the simpler one, and that's going to lead to the second way, which is more complex, and each of this is a question which leads to the next question. So essentially if we look at the sphere, we can form a coordinate system like this. We can form x and y here, and we can simply presume that this is a two-dimensional problem if we also presume that there is a 3 dimension here which is encapsulated in the 2 dimensions. So what we can do is that we can think this is a circle here. This circle is x square plus y square is r square, and there is a small region here of length dx, and the area of cross section of this region in yellow is pi y square. So I'm using the fact that essentially there is a circular cross section here, and this cross section is going to be given by pi y square. Remember, y is this particular radius here, and this y of course varies as the circle goes around this particular coordinate system. Now we can then essentially say that this dv is pi y square dx. That's this shaded region in yellow here, that is dx multiplied by pi y square. That's a small rectangle here. Now if we want to find the volume of the sphere, we have to integrate this between negative r and r, that is these two particular values here, and remember this is related to x, so x is the coordinate in this direction and we have dx here. Now once we have written it in this form, it essentially becomes a math model, and you can convert this into a simple integration problem. So of course we know that y square should be written in terms of x because that's what we have as the variable with respect to which the integration has to be performed. So we take this equation here for the circle, that is x square plus y square is r square, and from there we substitute y square is r square minus x square here. So we get this particular expression for the volume, and now I can very easily do the integration problem. So this pi r square term simply becomes pi r square x, and the negative pi x square becomes negative pi x cube by 3, and the integral bounds are minus r to r. So if I now put the value of r here in this particular expression, I will get pi r cube minus pi r cube by 3, and I have to then subtract this from the value of this expression when I put x is negative r. So I do that here. If I put x is negative r, this becomes pi r cube, but there is a negative sign, and this will become pi r cube by 3, but the negative will cancel with the negative, and so I will get a positive sign here for pi r cube by 3. So I have this expression here. Now I can see that I can simplify this expression. So there is a pi r cube here, there is another pi r cube here, so I get 2 pi r cube, and I see there is a pi r cube by 3, there is one more pi r cube by 3, both are negative, so I get minus 2 pi r cube by 3. And if I simplify this expression further, I take 3 to be common in the denominator, then I would get here 6 pi r cube minus 2 pi r cube, and that's going to give me 4 pi r cube by 3. So that's the volume of the sphere. So this is a simple derivation which you can do by using an integration only along the x direction. Now, of course, some of you may have seen that I'm using the fact that there is a circle here, and I'm using the fact that the circle actually has a cross section given by pi y square. So that leads me to the next question. So if there is a student who has finished the first two questions properly, or maybe there is a third student coming in, you can ask the third question which I'm going to pose next. So question number 3 says that derive the formula for the volume of the sphere of radius r, but don't use this fact that the circle is given by pi y square. So again you are asking now, that should not be used. Somehow the pi should come in through the general derivation using mathematics. So let's try to do this problem. So now we turn to three-dimensional coordinate system. So essentially we consider x, y, and z or z direction, and essentially we have the sphere here. Now the equation of a sphere is given by x square plus y square plus z square is r square. So this is the equation here. You can see this is an extrapolation of the equation of the circle, which is x square plus y square is r square. Now you have added the z coordinate or the z coordinate also. So if we now consider that there is a small cube here in this particular xyz coordinate system, this small cube would have a dimension, let's say dx, dy, dz, depending on the three faces of the cube. So essentially if we consider this cube to be, or this sphere to be in 8 different quadrants, then we can say that the volume is going to be 8 times the triple integral of dx, dy, dz. So this again is the math representation of the volume, and we can try to solve this problem here. So let's look at this volume expression out now, and let's see how we can actually calculate it. So you have to of course remember that when you are first looking at, let us say, the dz variable, then we have to express this from 0 to the z coordinate, and the z coordinate is going to be r square minus x square minus y square root. So that's what we have put here. Next we try to look at the y coordinate, and for the y coordinate we are going to look at r square minus x square, because here what has happened is that z has been taken care of in this integral, and so you have r square and x square in this particular setup. And finally when we look at the x coordinate, we simply have to integrate from 0 to r. So remember, I am only looking at the first quadrant here, which is the quadrant where x, y, z are all positive, and then I am simply going to multiply that particular volume by 8 to get the volume of the entire sphere. Now what I can do is I can typically write it in this form here. So here it is presumed that first you integrate with respect to z, then with respect to y, then with respect to x. So this is a typical multiple integral problem. Now let us take a look at this problem here, and I'm going to do this by part so that it's more clear. So let's first look at this part which is given in purple here, and we are going to try to do this. So we are going to simply take dz, and I'm going to calculate this I1 value, which is integral 0 to r square minus x square minus y square root into dz. and this immediately comes to root r square minus x square minus y square, because remember the integral of dz will be simply z, and then you simply put this value here. So this is the first integral, very simple value here. Now what I can do is I can take this v and I can put this value inside this. So I have got rid of the z coordinate here by this integration. Now the next thing is we concentrate on this integral part in blue, which is related to the dy value here, and so I have this integral which we give as I2. So again let us try to do this integral. Now remember, whenever there is a dy present here, you have to treat the x as constant, so that's something to keep in mind. Similarly here dz was present, so we treated x and y as constant values. That's how we got those integrals. So let us now look at this integral I2 here. So I2 is given here. Now from our knowledge of trigonometry, we can immediately make some substitutions which may simplify our life. So we can write that y is root r square minus x square sine t. And by doing that, I'm going to be able to simplify this to a form which is simply given by cos of t. And I can also immediately get dy is this particular value cos t dt. So again remember that x is here a constant. Now we also need to change the bounds of this integral. So we can see that when y equal to 0, t will be 0 because sine t will be 0. And then when y equals root r square minus x square, which is this value, then here sine t will be 1, so t will be pi by 2. So I can write this integral I2 as 0 to pi by 2 into this value here. And what I have done here is I have replaced y square with this particular value here, so that will become r square minus x square into sine squared t, and then the dy value has been replaced by this value here. Now you can see some simplification will happen. If I take r square minus x square as common here, I'm going to get 1 minus sine squared t, so that's going to give me cos squared t here, and here I'm going to get this value. So I am going to get r square minus x square out of this particular integral, because there are two such values both under square root, and then I'm going to get cos square t dt, because remember this is root cos square t, so this becomes cos t, and we multiply this by cos t to get this here. Now this particular integral 0 to pi by 2 cos square t dt you can very easily calculate. I think we have done in some of our very previous lectures in this math mania playlist, and you will get this to be pi by 4 r square minus x square. So this is the I2 integral. Now what we do is we have calculated the value of the I2 integral. So this integral has come out to pi by 4 r square minus x square. Now we go back to our volume expression here. We have calculated some of these integrals with respect to dx and dy. So now what we are left with is pi by 4 r square minus x square, and so this is the last integral I need to find, and this is with respect to dx. So this is very easy to find. I can immediately write this as x r square minus x cube by 3 by simply integrating these polynomials, and this is between 0 and r, and I can calculate this integral to be 2 pi r cube minus r cube by 3. So remember here there is a 4 here, so it cancels with 8 and you get 2 pi here. Here you get r cube minus r cube by 3 by substituting r, and when you substitute 0 you simply get 0 in both these terms. And I can immediately then simplify this further, and I get v is 4 pi r cube by 3. This formula of course was obtained totally by integration on the x, y and z coordinates, and we never assumed the fact that there is a circle out there and the cross section of the circle is pi y square. So that's something which is very important. Now sometime if you have a very precocious student, very smart student, you can ask him or her this question, and that's going to be a good way to check their knowledge of coordinate geometry, especially in the 3 dimensions. Now let's cool down with some simpler problems. So the question 4 is: a cylinder has a volume of 1 cubic meter. The height of the cylinder equals the diameter. What is the radius of the cylinder? Now sometime you need to have some simple questions also with you, because every candidate has to be asked some questions, and you have to make sure that each candidate is asked a particular math question to satisfy that requirement. So let us try to do this problem. So again the cylinder volume is given. That volume of the cylinder is pi r square h. So remember, that's the cross section pi r square, because it's a circular cylinder and it's multiplied by the height of the cylinder h. Now it's given that the height of the cylinder equals the diameter, so I can write h is 2r, and it's also written the cylinder has volume 1 cubic meter, so 1 comes here. So I very quickly have a simple equation, that is 1 equals 2 pi r cube, and so radius cube is going to be 1 by 2 pi, and therefore r is the cube root of 1 by 2 pi. You can calculate this in a calculator and you can get 0.5419. You can also do this on your phone. Finally, question number 5 is that the distance between 2 points in space is 10, and these points are given as 2x3 and minus 1 3x, and you are asked to find the value of x. So let's look at this question. This basically tests the student's capability to actually use the fact that what is the distance between any 2 points, and there is a very simple formula for that. So essentially you have to use this formula. The distance is given by 10, and the distance between these 2 points is actually the root of the sum of the squares, so of the differences. So you have 2 minus 1 square plus x minus 3 square plus 3 minus x square, and you take the square root of that. Now what I do is I can simply square both sides of this equation. I get 1, 2 minus 1 square becomes 1. I have x minus 3 square and 3 minus x square. I can then further simplify this. Remember, I can use the formula a minus b square is a square minus 2ab plus b square. So I get 1 plus x square minus 6x plus 9 plus 9 minus 6x plus x square. I can do some simplifications here. I get 2x square here. I get minus 12x, and I get plus 19, because 9 plus 9 plus 1 is 19. That is 18 plus 1. And then I bring this 100 from the left hand side to the right hand side, and I can write 2x square minus 12x minus 81 is 0. So I essentially get a quadratic equation, and then you can solve this quadratic equation. So let's try to do that. So we take this quadratic equation and then we solve it. So we get x is minus b plus minus root b square minus 4ac by 2a, and then I solve this equation here. So I am getting here, remember, b is minus 12 here. So remember, the equation has the form ax square plus bx plus c equal to 0. So a is going to be 2, b is going to be minus 12, and c is going to be minus 81. So with that I can solve this equation. I do some math manipulations, and then finally I obtain x as this particular value, which is 10.036 or minus 4.035. So essentially we get two roots of this equation. So there are two possible points or two possible values of x which are going to satisfy this equation here. So today we had a very brief introduction to some aspects of coordinate geometry which you can ask, especially 3D geometry. The equation of a sphere is very important in many situations. For example, if you are dealing with very basic aspects of space and so on, the various planets can be thought to be spheres. And also you can check out the student's knowledge as far as integration is concerned by some of these problems. So that's something which we discussed today. In the next lecture in Math Mania, I'm going to look at Laplace transforms in detail and how these can be used to solve ordinary differential equations.